Okay, this is a lecture on regression. This is the second lecture of two. So in many ways, this is going to be a review of what I covered in the previous lecture with just a little bit more new content. So recall that regression involves prediction of scores on one variable y using information from another variable x. And previously, we learned that we can do regression using z-scores. Okay, so where we have a standardized regression where we're predicting a z-score on y from a z-score on x. And in that equation, what we're going to do is multiply a participant's or a person's z-score on x by a standardized regression coefficient, which is equal to the correlation coefficient. Doing so gives us a predicted zy score. We can also predict scores using the original metric, otherwise known as raw scores. So in doing that, we're going to multiply a person's score on x by an unstandardized regression coefficient, but then we're also going to add in a regression constant, or A. So in this equation, a person's predicted score on y is the regression constant plus their score on x multiplied by the unstandardized regression coefficient. Okay, and so recall that this equation is the equation for a straight line, and we can graph that straight line in a two-dimensional space where the x variable is on the horizontal or x-axis, the y variable is on the vertical or y-axis, and our values of a and b then determine where that line will intersect the vertical y-axis. Okay, so our regression constant is also known as our y-intercept, and then our unstandardized regression slope or our unstandardized regression coefficient is the slope of that regression line, and that will tell us how much that line is sloping, either sloping up from left to right in the case of a positive relationship, okay, and it's going to capture that rise over the run, or if we have a negative regression coefficient, we have a negative slope, so we know that that line is going to slope down from left to right. So in order to come up with those values for the regression constant and the unstandardized regression coefficient, otherwise known as the slope, we've got two formulas that we're going to use. So we come up with the regression coefficient by taking the correlation coefficient, multiply that by the standard deviation of y over the standard deviation of x. And here's the way I like to think about this. So using raw score prediction, we're looking at the relationship between an x variable and a y variable, and they can be measured on completely different metrics. So we might be trying to predict income, our y variable, from GPA. And the metrics of those variables are very different. GPA only ranges from 0 to 4. Income can range from, unfortunately, $0 but to some very, very high numbers. So typically a standard deviation might be in tens of thousands, whereas for standard deviation for GPA, it's going to be in tenths of a point. So of course the correlation coefficient captures the strength of the association between those two variables, but then multiplying by the standard deviation of y over the standard deviation of x, we can say kind of unstandardizes the regression coefficient, and it does so in a way which takes into account the rise over the run of that pattern of data. Okay, so our regression coefficient is that slope of that regression line, and so we need to have the rise and the run of that line take into account the metrics of the variables that we're using in our relationships, or the metric that we're using to measure those variables. So doing that with the standard deviation of y over the standard deviation of x captures the rise of the line over the run of the line. Okay, now once we have that B term, okay, the regression slope, otherwise known as the unstandardized regression coefficient, we use that term to come up with our regression constant. Okay, this is a constant value. And so you can think of when we're trying to come up with somebody's predicted y, we have kind of a starting place. We have this constant value that then we're going to then increment by their x score multiplied by the regression coefficient. So we come up with that regression constant by taking the mean of y minus that regression coefficient times the mean of x. Okay, let's just plug in some numbers to have another example that kind of has some context to it. So in this example, given the following information, predict how a student will score on a statistics exam if she studies for 6 hours. And let's just say that we've got some descriptive statistics about the number of hours of study. So our predictor variable, our x variable, we know that the mean is 4 with a standard deviation of 2.5. So in our sample of students that we use to collect the data, the mean number of hours studied for the exam was 4. And the score on the statistics exam, so our criterion variable or our outcome variable y, the mean was 90 with a standard deviation of 10. I would love it if I had exams that had a mean of 90, I can tell you that. Okay, and the correlation between the two is 0.7. Okay, so there's a strong association between studying and performance on the exam. Okay, so what we want to be able to do is, given the relationship between hours of study and score on the exam, knowing the mean as well as the standard deviation, we want to be able to come up with a prediction equation so that we can be able to predict based on already collecting data, that then when we have a new student, we can be able to tell them, hey, if you study 6 hours, this is our prediction for the score that you will get on the exam. And we're able to do that with our regression equation. So what we need to do is we need to come up with our values of A and B, and we need to find B first, of course, in order to get our value of A. So, okay, so yes, first we need to figure out B. We'll do that using the formula that I previously described. So we're just going to take our correlation coefficient of 0.7, multiply that by the ratio of the standard deviation of y, which I pulled from right here, standard deviation of y, and then the standard deviation of x. Okay, so that ratio, 10 divided by 2.5 is going to be 4. So multiplying 4 by 0.7 gives us a slope of 2.8. Okay, so I'll just kind of pause right here because that slope is directly interpretable, or we can say that the unstandardized regression coefficient is directly interpretable. What it means is that for every 1 unit increase in x, this is the associated change in y. So here we've got a positive coefficient, so we've got a positive change in y. Okay, so another way of saying this in the context of the problem is for every additional hour studied, we predict a improvement in exam score by 2.8 points. By 2.8 points. Okay. So the next thing, now that we've got B, we can use that to figure out A. We'll do that using the formula that I previously described. Really, it's just a matter of substituting in values. So here's our regression coefficient that we just determined. Okay, we've got our mean of y, which is 90, which I just pulled from here. Okay, so we're then subtracting the mean of y. We're going to subtract our regression coefficient multiplied by the mean of x. Okay, so it's 90 minus 2.8 times 4. So we need to figure out what 2.8 times 4 is and then subtract that from 90. When we do that, we established that the regression constant is 78.8. That also is directly interpretable. What it means is that in a general term, the regression constant is the predicted value of y when x is 0. So when the value of our predictor is 0, our regression constant is our predicted value of y. In the context of this problem, what it means is that our prediction is that if you're a student and you study 0 hours for the exam, your predicted score will be 78.8. Sounds pretty good, doesn't it? Kind of an unrealistic example in hindsight. But that's how we would interpret it. Okay, so now we've got our two pieces of information. We've got these two values for our regression constant and our regression coefficient, and we can use that to plug in different values of x. Okay, so our original question was, we wanted to know what would we predict a student's score on the exam will be if she studies for 6 hours. So that's our value of x, and we can just plug that straight into our equation. Okay. So we know that if she studies 0 hours, the starting place is 78.8. So to what extent will that score be incremented or improved for each additional hour of study? Well, we know that for every 1 hour, a score improves by 2.8 points. So she studies 6 hours, so it improves by 2.8 times 6. Okay? So that would result in a prediction of a score of 95.6 for a student that studies 6 hours. What about if a student studies for 4 hours? Let's plug in. Okay, same equation, our regression constant is 78.8. We're going to plug in an x of 4, and we get, when we do that, you'll get a result of 90. So this illustrates an important principle of regression, which is this. When a person or when an observation scores at the mean of x, the predicted value on y is always the mean of y. Okay, so we predict that for an x value at the mean of x, the predicted y is always the mean of y. Another way of saying that is that our regression line always passes through the mean of x and through the mean of y. So when we're going to plot our regression line, that line, okay, regardless of how it slopes, okay, that line is always going to pass through the mean of x and the mean of y. Always. That is a principle of regression. Okay. And then what about 2 hours? Okay, so we can see that when we plug in 2, we get a prediction of 84.4. So if the data that we use to create our prediction model are reliable, we now have a system for giving study advice to similar future students. So this is a really great use of regression, really otherwise known as prediction, is that you do a study, you collect data, you assess the relationship between two variables to the extent that there is a reliable correlation. And by reliable, we mean really strong and statistically significant, although you can have a reliable correlation even though it isn't statistically significant. So let me just say that if we have a statistically significant correlation, to the extent that it is strong, we know that we'll have a good prediction model, and we can come up with a regression equation that can be used to then predict an outcome by measuring only one variable. Okay, so I'd be able to say, based on previous data, if you would like to achieve a particular score on this exam, you should study at least this number of hours. But it's important to keep in mind that it's only a prediction, a best guess. It doesn't determine how well a student will actually perform. And if you kind of put on your thinking cap, certainly there are other variables related to performance on an exam. It's not just study hours. It could be the number of hours that you sleep the night before the exam. It could be, overall stress levels. So this turns into more complicated research questions, and it turns into more complicated statistical analyses which I will give you just a little bit of that towards the end of the lecture, but just to foreshadow. Okay, so how do we evaluate our regression model? That is, how much faith should we put in the accuracy of our prediction model? It really depends on how much error we have in our predictions. Okay, so the quality of our regression model is really based on the strength of the association between X and Y. When X and Y are strongly correlated, that really means that those, in our scatter plot, those observations for each person, their X and their Y scores, will cluster closely together in a straight line fashion. Okay, and that regression line is really capturing that straight line association. Okay, but whenever there's a less than perfect correlation between the two variables, there will be some error because our regression model, it's a simple model. It's just a simple straight line. We shouldn't be too hard on it. Okay, so all it can do is be a simple straight line. It's not possible to go weaving through all of these data points. It's just a simple straight line. Okay, and so with that in mind, in some cases it's going to do a very good job, and in other cases it's not. Okay, and how good of a job that straight line does will of course depend on the extent to which those dots fall in a straight line pattern to begin with. Okay, which is to say that the stronger the association there is in the first place, the better the straight line model will do at not having any error, okay? And the extent to which these dots depart from that straight line relationship, such as when there is a weaker correlation, the more error there will be in using a straight line as a prediction model. The way to evaluate just how good that model is to capture those errors in prediction from our model and the data that was used to generate that model. Okay, so our data that was used to generate the model are the actual scores that we get from people. Okay, when we collect their data, say in our study, so every person in our example actually had a number of hours that they studied, and they actually had their performance on the exam. Okay, and again, you can think about, well, it's not going to be a perfect relationship. You've got, the person that studies the most, okay, and in this case, they're, the highest score, but not a lot. And here you've got examples of people that that perform less well, even though they studied more than these folks right here. Okay, so it's only a single variable, and there's going to be some error in prediction. The way that we capture those errors are by taking the squared error. So we're going to look at the difference between the actual score and the predicted score, and then we're going to square that. The reason we do that is that it is a principle of the best fitting regression line that those errors in prediction cancel to zero. So if we were only going to try to evaluate our model by saying like, well, let's just sum up all of our errors, and we'll capture errors by our actual data point minus the line. What you can see is that sometimes we underpredict and sometimes we overpredict. Okay, here's a good example of underpredicting for this particular data point. Here's an example of overpredicting for this data point. So these red lines, in this case, represent underprediction, and these red lines represent overprediction. With a best fitting model, those underpredicting and overpredicting errors balance out to zero perfectly. Okay? The parameters of this line, the A and the B, are established via calculus, and those numbers are generated by saying what is the A and the B that will create a line such that our regression errors where we underpredict versus overpredict will cancel out to zero. So in evaluating any line, regardless of whether you've got a strong correlation or a weak correlation, if you would just look at the errors in prediction, those errors will always sum to zero. So what we have to do is we have to square those errors. Okay? So if there's just a little bit of error, when we square it, there's still just a little bit of error. If there's a lot of error, when we square it, there's a lot of error. So squaring those errors still capture whether there's a little or a lot of error. Okay. So the quality of our model is captured by our sum of squares error, okay, where we're going to sum up those squared errors in prediction. Okay. But that number in and of itself is not directly interpretable, and the size of the sum of squares error will depend on the metric of the variable. Okay, so if we're using small numbers, we'll get a small sum of squares. If we're using big numbers, we'll get a big sum of squares. So what we have to do is we have to evaluate sum of squares error based on the total amount of variability in y using the adjusted for the metric that is being used to measure y. Okay. So in order to understand this quantity, okay, we can't just directly interpret sum of squares error. We need to have a baseline for comparison. So the way of looking at this is we would say without our regression model, okay, our best guess is simply the mean. So let's go back to our example. If we wanted to say, what do you predict a student's score on the exam is likely to be? And you don't know how much they studied, okay? Your best guess, which means the guess that is likely to be off by the smallest amount, okay, is the mean. So in this case, we'd say, well, if I know that the mean on the exam is 90, for this particular student, I'll just guess 90. Well, what about that student over there? Well, knowing no other information about that student, my best guess is going to be 90. I'm probably not going to be right, but I'll have the best chance of being accurate, or at least I'll have the best chance of having the least error in prediction if I just guess the mean for everybody. Okay, so that's our baseline. And there's a certain amount of error that would be associated with just guessing the mean for everybody. But now if we know we've got a predictor variable and we're going to use that predictor variable, the question is, can we do better than just guessing the mean for everybody? So for instance, if study hours is correlated positively with exam performance, we can say, okay, well, if it's positively correlated, highs go with highs, low goes with lows. So if I know that they're above the mean on study hours, I'll guess that they're above the mean on exam performance. If they're below the mean on study hours, I'm going to guess that they're below the mean on exam performance. Okay? And so that ends up being a good model to the extent that X and Y are correlated. So to the extent that study hours and exam performance are correlated, we should be able to do better than just guessing the mean. Okay? So our baseline is the mean. And using the mean, our error in prediction is just each person's actual Y minus using the mean as our guess. Okay? And you'll notice that that's the same sum of squares that we get when we calculate the variance in Y. Okay? So the worst model, okay, we can say that the very worst regression model that we could have is just using the mean of Y, and the most error we could have is the sums of squares total, which is used to compute the variance in Y. Okay, so kind of in more general terms, the total amount of variability in Y represents the total amount of error that we could have. Okay, and that's what we would have when we use the mean. Okay, so can we do better? You'll notice from this equation that if we will have some error with our regression model. Okay, and the more error we have, the less we reduce our total amount of error. Okay, let's just sub in some numbers here. If we've got a perfect model, a correlation of 1, error will be 0. Okay, and so in this formula, we'll then take sum of squares total minus 0 error from our perfect model. So we'll end up with sum of squares total divided by sum of squares total. And that will result and an R squared that is equivalent to 1. Okay, so we have a 100% proportion reduction in error, going from all of the error that we could have to 0 error. We've reduced error by 100%. What if our sums of square error is exactly the same as using the mean? Okay, in other words, what if our regression model is the mean? Well, then sums of squares error is equal to sum of squares total. So sum of square total minus sum of square total is 0, okay? And then we have an R squared of 0. So we have a 0 reduction in error if we just use the mean. So our R square can range from 0, which means we do know better than the mean, to 1, which we can only have if we have a perfect correlation between the data. So our R square is going to be somewhere in between, and it will be closer to 1 to the extent that we have less error. Okay? And we have less error when we have a stronger correlation between the two variables. Okay? And so we can think of an R square as reflecting the amount that we've reduced the error in prediction from the mean. Okay? So therefore, the higher correlation we have, the smaller the error, and the more accurate our predictions, because the more variance we've been able to explain or account for. Okay? So reducing error in prediction is the same way as saying we've now explained or accounted for variability in Y. All right, so again, the lower the correlation, the less faith we have in our regression model. When there is 0 correlation between two variables, our model is no more accurate than simply using the mean of Y. Okay? And that will be the case only when the correlation between X and Y is perfectly 0. So long as there is a non-zero correlation between X and Y, we'll do better than the mean. I'll repeat that. So long as there is a non-zero correlation between X and Y, we'll do better than simply using the mean of Y. How much better? Well, we can evaluate that using R squared. All right, let's shift to the last topic, which is multiple regression. So I kind of foreshadowed that in trying to understand different social and behavioral and psychological phenomenon, there's usually multiple factors or multiple influences on different outcomes, like attitudes and behaviors. So multiple regression is a technique to be able to explain the most amount or the highest amount of variance in our outcome Y as possible. Okay? So in other words, we want the most accurate prediction model possible. And our prediction improves when we include additional predictor variables. And this technique is known as multiple regression. This is just a procedure for predicting scores on an outcome using scores on 2 or more predictive variables. So in bivariate regression, we have the standardized form. Predicted zy equals the standardized regression coefficient times zx. Multiple regression, we can think about it as we've got a y, an outcome that we want to predict, and we're just going to predict that from multiple variables. So not bivariate, just 2 variables, but we're going to predict that from multiple variables. Okay, and we've got both a raw score form as well as a standardized form. And it's very common in multiple regression to look at a standardized form of the regression equation. And so we are not going to go over really not going to go over any of the math behind multiple regression. This is an advanced technique that you'll learn in an advanced stats class, or if any of you go to graduate school, you'll learn it there. But for the purposes of this class, it's really just to let you know that this is a technique, it is a thing, and when you go on and take more advanced classes in the social and behavioral sciences, you might end up reading primary research papers that use this technique, and this will hopefully allow you to look at that and say, oh, I know what they did. They did a multiple regression. They're trying to explain or predict an outcome using multiple variables or multiple predictors. Okay. So in this case, we're trying to predict a student's exam score based on the number of hours that they study, the number of hours that they sleep before the exam, and let's just say the number of alcoholic beverages that they drank the night before the exam. Our standardized regression coefficients are interpreted in much the same way that we interpret the regression coefficients in the bivariate case. Okay, what these coefficients express is whether we have a positive or a negative association between a predictor and an outcome. So you can see that because these standardized regression coefficients, okay, otherwise known as betas, I'll just switch and start describing these as betas. It's less of a mouthful. Okay, because these betas are positive, we know that there's a positive association between study hours and exam scores. There's a positive association between hours of sleep and exam scores when considering the effect of the other variables on exam scores. Okay, so it's always in that context. We know that this equation tells us there is a positive association between hours of study and exam score when also considering the effects of these other two variables on exam score. Okay, in contrast, we see that there's a negative association between number of alcoholic beverages consumed the night before the exam and exam score when considering the effect of the other two variables as well. Okay, and so what we're able to do is still come up with a prediction equation, substituting in different values along the lines of, okay, I know if this person scored 1.5 standard deviations above the mean on study hours, one standard deviation above the mean on sleep, and scored at the mean on number of alcoholic beverages consumed the night before, that will lead me to predict that this person will score 1.22 standard deviations above the mean on the exam. Okay, so with this standardized prediction, the X scores are all Z scores, okay, and so can be interpreted as a number of standard deviations, and same with the Y score. It's going to be a ZY, and the interpretation is based on number of standard deviations above or below the mean. Let's just do another example. Okay, so somebody that scores 2 standard deviations above the mean on drinks, but then 1 standard deviation above on sleep and 1.5 standard deviation above on study, we would predict only scores 0.54 standard deviations above the mean, which suggests, in practical terms, that if you're above average on sleep and study, that can compensate for being well above the mean on, say, partying the night before, but certainly there's an influence. So you can see the kind of combined effects of multiple influences or multiple factors on predicting an outcome. And that's really the benefit of this technique, is we can have more sophisticated research studies that look at the influence of several different predictor variables on an outcome. Now, there is an important difference between multiple regression and bivariate regression. In the bivariate case, the beta, okay, the standardized regression coefficient, is exactly equal to the correlation. Okay, so when predicting y from x in the bivariate case, the beta is exactly equal to the correlation between x and y. Okay, but that is not the case in multiple regression. So when predicting y, okay, in standardized form, but when predicting zy from zx1 and zx2, the two different betas are not equivalent to the correlation between each of the respective x variables and the y variables. Okay, so this beta is not equal to the correlation between x1 and y, and this beta is not equal to the correlation between this x and y. Okay, when there is a non-zero correlation between x1 and x2, and the reason is because there's usually some overlap between predictors. So in the example that I just went over, you can imagine that if x1 is study hours and if x2 is sleep, there's bound to be a relationship, okay? There's bound to be a correlation between students that study more and students that are more likely to get a good night's sleep. Okay. Now, we can think of like that relationship could be, honestly, that relationship could be positive or it could be negative. So if we think that everybody in our sample is cramming, then if we got people that are staying up all night cramming, then study hours is going to be negatively associated with sleep. Alternatively, if we think that people are spacing out their studying, then the really good students who have been studying for 3 or 4 weeks, okay, let me be more realistic. They've been studying for a week, and they've been spacing out their studying all that week, so that they don't need to be cramming the night before the exam. Okay, there should be a positive relationship between the number of study hours and hours of sleep. Either way, there's usually some overlap between the predictors. And in that case, each beta, each standardized regression coefficient, represents the unique and distinct contribution of each variable, excluding the overlap with the other variable. Okay? So what this says is that there's some overlap between study hours and sleep, okay, that is kind of jointly responsible for predicting exam score. And what that beta is going to do is say that the beta is only this unique part of study hours that doesn't consider or has removed the effect of sleep. And then same thing, this beta 2 is the unique effect of hours of sleep having removed or taken away from consideration this overlapping part. Okay. It's possible to calculate the multiple correlation, which is a big R, between the criterion variable y and all the predictors together. Okay. This R takes into account the overlap, so big R is usually less than the sum of all the little r's or the little correlations. So in other words, you might say, well, if study hours is correlated at 0.5 and sleep is correlated at 0.4, the multiple R should be 0.9, right? It doesn't work that way because of the overlap. You might also say, how is it possible to have a single correlation, big R, when there's two variables? How does that work? Well, the way that works is we look at the correlation between the actual y and the predicted y. And that's the way that the relationship between actual y and the predicted y, based on the multiple correlation coefficient, allows us to then come up with the multiple correlation R. But really, that's a topic for another class. What I want you to know is that there is such a thing as a big R, which captures the strength of association between an outcome and a set of predictors. Okay, right. So the multiple correlation is the strength of association between an outcome, otherwise known as criterion, and all the predictor variables taken together. The range is 0 to 1. It can never be negative. So even when there is a negative association. Okay, why is that? Because what we're ultimately looking at is the correlation between actual y and then predicted y's, and those will always be positively associated. And then the interpretation is the same as R, such that higher values equal stronger association. So I share this mostly just for, again, when you go on to more advanced classes, you might see this multiple correlation R statistic being reported, and it's mostly important that you're able to look at that and interpret that, is to say, oh, okay, so there's a multiple regression that was performed, and what the researchers are reporting is the overall strength of association between the set of predictive variables that they looked at and an outcome variable. It is more common, though, to report a big R squared. Okay, same interpretation. It's the proportionate reduction in error, or otherwise known as the proportion of variance accounted for in Y by all the predictor variables taken together. Okay, so same thing. Higher numbers of R squared mean a more accurate regression model. Values of R squared can only range from 0 to 1, and these are effect sizes. So I should say 0.02 is a small effect, 0.13 is a medium effect, and 0.26 is a large effect. Okay? So these guidelines are based on social and behavioral sciences. And so what it's really saying is that when we have a set of predictors, if we can explain 26% of the variability in an outcome, that's considered a large effect. We're doing a good job. Okay? So in social and behavioral sciences, because of the variability in human behavior, if we're able to explain 25% of the reason why scores deviate from a mean, that's considered doing a good job. That's a large effect. Okay. And that is it. So hopefully this was a good recap and refresher on bivariate regression, and that in introducing multiple regression, this will give you more confidence in the classes that you're currently taking, or classes that you'll take in the future, like a research methods class or more advanced classes in your field of study, that you can look at a research report and see a multiple regression and generally understand what was done.